Okay, let's introduce some basic definitions within graphs. So first of all, graphs are probably one of the most widely used data structures in the whole of computer science. So I cannot think of a single problem space which does not touch upon the graphs data structure. Doesn't matter which domain you tackle. And therefore, it is very important for you to get a good grasp of graph theory. So what is the definition of a graph? So a graph G is a set of, so set V of vertices are also known as nodes. So nodes or vertices. Okay. Graph is a set of vertices and a set E of edges that connect them. So we saw a rooted tree, right? A rooted tree is, in one sense, a particular kind of graph. So what would be the key difference between a rooted tree and graph? Does any of you remember the definition that we gave of a rooted tree? Because here also we are talking about a set of vertices and set of edges that connect them.
The rooted tree specifies one particular parent, while the graph does not appear to do so.
That's
one
right.
particular root.
And what is it that is making it a tree? So you said like one distinguished node is a root. And what is it that is making it a tree?
All the nodes thereafter are connected.
Say that again?
All the nodes thereafter are connected.
Okay, all the nodes are connected. But what is the specific property that makes it a tree?
Each node has only 2 leaves.
It doesn't have to be 2. That's a binary tree, right? At max, there are 2 children at max, right? How did we define a tree when we were entering into the topic of trees? You take any 2 nodes. Could there be more than one path?
No, so there has to be exactly one path between
one. Exactly. So that is what is the specific characteristic of a tree. Otherwise, both trees and graphs, you can say they are a bunch of nodes and you connect them through edges and then you get essentially that structure. But in graphs, that's exactly what you're allowing. You're allowing multiple paths to exist between nodes. All right. So oftentimes it is represented symbolically like this: G equal to V comma E, where V is the set of vertices and E is the set of edges. So this is ordered pair of a set of vertices and edges. Okay. Okay, so suppose I write T equal to V comma F. Okay. So in fact, T and G can have the same set of vertices, right? So that's why we can say that this is T, this is indicating that T and G have same set of vertices. Hence we are using the same set V here. You can see the only variation is the connectivity. Now, there are two types of graphs. So this is another distinctions. So there are two types of graphs. One is called directed graphs. They're also known as digraphs, and undirected graph. So in other words, you do a bunch of nodes and you connect them with an arrow. You know, this is a directed graph. And if you have nodes, but you do not necessarily draw an arrow, no directional sense, then this is an undirected graph. So you saw that in trees, there was no notion of directed or undirected. Okay.
But weren't there like parent pointers and child pointers? Doesn't that indicate a sense of directionality?
Right. So because of the parent and the child relationship, in one sense, you can see the trees are always directed. There was no notion of distinction between directed and undirected. Right? So digraph or directed graph is where every edge E is directed from some vertex V to some other vertex W. So you have V to W connected by edge E. So then E can be written as E here is equal to V comma W, and this is an ordered pair because that shows the direction. So this V is the source, and this is the destination. Okay, what is an undirected graph? Where E is an unordered pair. So this is an ordered pair here, but in the undirected graph. So that means that if you have E, V comma W, which is the same as W comma V. So you will draw two nodes, V and W, and this would be your edge without any direction. So what would be a common use of a graph? Can you think of any use of graph where you want to just pull a bunch of vertices and edges connecting them? Can you think of something? What would be some common examples?
Like a subway system or like the transportation system representing that could be used by
Very good.
graphs.
Yeah. So transportation system where like Google Maps, right? It's ultimately just a series of nodes and connections. And you can also
Like neural networks.
yeah, networks, very good. And in fact, one of the exercises that we will do in the lab will try to implement a mini version of Google Map. In one of the labs, that's what we will do to get a sense of how we can find the proper direction between two points of interest. We'll do an exercise like that. In compilers, particularly, there are many different varieties of graphs. Like the values typically flow through the variables. And the variables, when you're assigning, and then there are reads and writes going on. So one can draw the whole graph of dependencies between those variables. So dependency graphs is a very common usage. So the point is that the graphs are everywhere. Doesn't matter which field you take. Like for example, if you take the field of deep learning, so then you, as Chris, you mentioned networks, like the whole convolutional neural network. That whole representation is through graphs, like CNN networks. Okay. So an important point to note here is that the multiple copies of an edge is forbidden. And digraphs, the directed graphs, can have both VW and WV. And you can have self edge, which would be V. So in the directed graph, it is more obvious like this. In the undirected graph, it may look like this. So you will have V and there's an edge going around. What is a path? So similar to the trees, so path is a sequence of vertices with each adjacent pair connected by an edge. If graph is directed, then edges must be aligned with the direction of the path. In other words, when you have a bunch of nodes going on, and when we are talking about taking a path from here to here, the path cannot be in the reverse direction. It has to go something from here along the direction of the arrow. So this is a path between the two nodes.
Wait, isn't the path the shortest walk to the other vertices? Isn't that like a important point or not?
It doesn't have to be shortest. It has to be called out.
But
If it is not calling out shortest path, it's just saying path, it can be any path. So if it is
Okay.
shortest, it would be called out. The length of path is number of edges again, okay? The same thing that we saw in the trees, the number of edges in the path. All right, so obviously, like when you are having just a single node and we are going a looping around, right? The length of this path is going to be equal to 0. And another important point is that path can revisit a node and an edge. Okay, so path can even revisit. Okay. Strongly connected. So what is a strongly connected graph? If there is a path from every vertex to every other vertex. What would be an example of that? So take any vertex here. It's possible to go from one vertex to another. So therefore, this is a strongly connected region. So typically the strongly connected region turns out to be a loop. And in the case of an undirected graph, the strongly connected graph for undirected is simply called connected. For undirected. Okay. So one important point is that that for strongly connected paths, if there is a path from every vertex to every other vertex. So in this case, if I am drawing, let's say, two nodes, so there is a clear path between the two. Now, if I draw in the undirected case, I have to draw something like this, right? Drawing another one doesn't make any sense. So this distinction you have to keep in mind, that if there are two nodes, then the strongly connected region or connected graph just implies having an edge between the two. Okay, so I think we can stop here for today. I think I went way over time, but I wanted to at least introduce some notion